Another context that comes up decently often when looking at optimization problems is those where you can represent two quantities mathematically, basically as equations, and then you're just trying to see how close they get to each other. You're trying to see how far apart they can get or how close they can get. In this case, that's what we're doing with this linear equation that we have, this y equals 3x plus 4, and a point. And we just want to see what is the point at which that line is closest to the point 2, -1. Now, to help you kind of visualize what all is going on here, this is what it would look like on the graph, where we could graph that line and we could see the point there. Now, looking at it, we would guess that our winning number would be somewhere in here, right? Well, we're going to need to find some way to actually figure out exactly where that is. In order to do so, we want to minimize the distance between the line and the point, which means we can actually write an equation then for distance. So we're going to start by doing that. We're going to write an equation for the distance between the point and the line. So to write this formula, what I'm going to do on my visual graph here is I want to be able to turn that into a right triangle so that then D becomes my hypotenuse. That allows me to then use Pythagorean Theorem. Basically, this is just a form of the distance formula that we're using here. And so that means that we're going to be doing, let me go ahead and just for the moment call that A and B so we can kind of see how this is going to get built. We know then that D squared would equal A squared plus B squared if we use those names there. So seeing that, I could then start figuring out how I'd figure out side A and side B. So like D squared would be A. Let's see here. A is, looks like that's the difference between the y coordinate and -1 down here. So I could actually figure that out then by doing y minus -1. Well, I don't really want to write minus -1, right? So let's just call that y plus 1, right? And then plus the b value. That's how far we're going over here. So if we're doing that, let's see here, that looks like that'd be the x value, the x coordinate of our point here, minus 2. And so then let's go ahead and call that x minus 2 in there. By the way, if you are saying, no, it's not x minus 2, it's 2 minus x. True, but notice we are squaring this, so the actual sign of that won't change anything. So this is the equation that we now want to minimize because we want to figure out what's the smallest distance we can get. But right now we have 3 variables involved, and that's where we are going to do that substitution piece to help us out. Now in this case, the part that we can substitute is the actual equation that we have for the line. We know that that's what y equals. Y equals this 3x plus 4. So I'm going to plug that into my equation. So we're going to go d squared equals, but instead of y, it's now going to be 3x plus 4. And that's still plus 1 squared. Everything else is the same here. All right, I can clean up that first parenthesis, right? So let's go ahead and do that. So d squared then would equal 3x plus 5 squared. And everything else is still the same. All right, now I'm looking to be able to find the derivative. And now that there is just those few variables, I can actually do that. And so if I find the derivative with respect to x, then the derivative of d squared would be 2d over dx. Okay, I don't want to deal with that, do I? Okay, rather than making it d squared equals, let's clean that up and just make that d equals before we go too much further. Then taking the derivative is going to be easier. All right, so I can turn that d squared into d by taking the square root of both sides. So we're going to go ahead and take the square root then of everything that I had there on that right side. So the 3x plus 5 squared and the x minus 2 squared. Okay, now we could find the derivative and not run into trouble. By the way, again, a little side note, notice I did not include the plus or minus in front of the square root here. Again, that's only because distance is always positive. Because of the context of this problem, we know that it has to be a positive distance. Technically speaking, when we take the square root of both sides, yes, we do include the negative as well. It's just the context told me I didn't have to here. All right, finding the derivative. Now I can do the derivative of d, and I can now do the derivative of this big old square root on the right-hand side. It is at this point that a seemingly very simple problem starts to take on a certain level of complexity, because you'll notice that we're going to end up having to use chain rule here. And just to make it clear, actually I'm going to get rid of that d prime. We're just going to call this d for the moment, and I'm going to show one more step here, and I'm going to write this whole thing as to the power of 1/2. That can help us to remember how and why we're finding the derivative that we are. Although, now that I look at finding the derivative with all that squared on the inside, that also looks like a bit of a pain, right? So while I could be taking the derivative right now and be using chain rule within chain rule, I think I probably can make my life a little bit easier yet by doing even more cleanup. So let's do another level of cleanup here. I need to do this 3x plus 5 squared so that I can get rid of the function within the function here. Now remember, when you do this, this is not going to be 3x squared and 5 squared. You actually need to treat it as 3x plus 5 times 3x plus 5 and multiply it out, where you multiply everything in the first parenthesis by everything in the second parenthesis. If you do that correctly, you should end up with 9x squared, yes, but it will be plus 15x plus 15x, which is 30x plus the 25. Do not forget about that middle term, or it will give you trouble. All right, and then we're also going to do the same thing by multiplying out the x minus 2 squared. And when you do that, you should end up with x squared minus 4x plus 4. And so then I can go ahead and put those parts in up here in my formula. So then that's going to become 9x squared plus 30x plus 25 plus x squared minus 4x plus 4 all to the power of 1/2. All right, now that I've gotten to that part, I can go ahead and combine like terms on the inside there so that I do end up with something simpler, because right now it doesn't look all that simple. And so then that will turn the whole thing into 10x squared plus 26x plus 29, still all to the power of 1/2. While we still have a fairly complicated looking equation here for finding the derivative, it at least is not going to be chain rule within chain rule. It's just going to be one iteration of the chain rule here. So let's try this one more time. D prime, finding our derivative. Hopefully now we've made it as easy as we can. So chain rule, we're going to do 1/2 times the exact same thing, so 10x squared plus 26x plus 29. But now we subtract 1, of course, from the original exponent because we're using power rule. And so then 1/2 minus 1 is a negative 1/2. But then remember chain rule, so we still have to multiply it by the derivative of that inner function. So we're going to be multiplying it by the derivative of the quadratic there. When we do that, we end up getting 20x plus 26. All right, we found our derivative. Last thing we need to do here with it is we need to solve it to see when that equals 0. And as I'm setting it equal to 0, I'm going to go ahead and clean this up a little bit here. So I can see that I'm going to end up with a fraction, so I can go ahead and build in my fraction. Then I can just put what's on top and bottom on bottom. And in my fraction, I have a 2 on the bottom from the 1/2 there. So go ahead and put that in the bottom. And then my exponent here is negative. So that means that's also going to be on the bottom of my fraction. So this is going to be the 10x squared plus 26x plus 29, all to the power of 1/2 on the bottom. What's left on the top then? Well, this 1 is from our fraction, but also this 20x plus 26, because that is not to a negative exponent. And so we still would have that on the top of our fraction. Now, as you look at this, if you're thinking, wait, can't we turn this 1/2 power into the whole square root? Yes, you can. And you certainly would be welcome to do so. However, it turns out you don't really need to in this problem. Because if I'm looking at a big old fraction like this, and I want the whole thing to equal 0, really I only have to make the top 0. Because 0 divided by anything equals 0. Whereas anything divided by 0 equals the world implodes and life ends as we know it. It's impossible. We cannot do it. And so because we cannot divide by 0, we don't have to worry about what makes the bottom 0, as long as it's not our answer. We only need to worry about what makes the top equal 0, which just made our lives a whole lot easier, because then all I have to figure out is what would make 20x plus 26 equal 0. And that's going to be a lot simpler to solve than what it looked like before. And again, I can do that because I'm just trying to make the top equal 0. Because as long as the top equals 0, the whole thing will equal 0. All right. So to solve this now, we would subtract the 26 from both sides. So then we have 20x equals negative 26. And then we could divide both sides by 20. And we end up with x equals negative 1.3. All right. That is the x-coordinate of the point that we are looking for. Now, we still want to figure out what the y-coordinate is, because it's asking us for the coordinates of the point that is closest. Remember, when we started this problem, we had the equation y equals 3x plus 4. That's the equation of the line that is going close to our point. Well, I can then take this x equals negative 1.3 that I just found, and I can plug it in there. So to find my y-coordinate, y equals 3 times negative 1.3 plus 4, which solves out to be 0.1. And so the coordinates of the point that is closest to our given point on that line is negative 1.3 and 0.1.